In this straight chem session, I'm going to walk you through with some problem solving in bomb calorimeter. This is the diagram of a bomb calorimeter. It has a thermometer, it has ignition wire which will heat up the sample inside, and the sample will be burned completely in excess oxygen, and surrounding the bomb inside you have water, and the stirrer on top will stir the water inside so that the heat will be distributed evenly inside the container. Other name for bomb calorimeter is constant volume calorimeter. And also, a few basic for thermochemistry that you need to apply in order for you to be able to solve some problem solving is the heat released by the system, the heat released by the reaction or system, which is represented by Q released, will be the same as the Q being absorbed, the heat's been absorbed by the surrounding. There are 5 possible Q absorbed situations. Number 1 is when you have Q, your heat, equals to m small c delta T. Number 2, when you have your Q equals to big C delta T. And then number 3, when you have your Q equals to mass times with the small c specific heat capacity times with delta T plus big C delta T. And number 4, when you have Q equals to mc delta T plus m small c delta T. And finally, the 5th possibility is when you have your heat absorbed, can be represented as the heat capacity times the change in temperature plus with the heat capacity times with the change in temperature. So we have 5 possibilities over here, but the one that I am marking with the star sign, those are the most popular ones that will be used in exams. Okay, so when you look at the start 1, 2, and 3, these are the most common, the most popular, going to be used in your examination. But note that it is not impossible for the examiner or the question wants you to find out for this type of Q and that type of Q. So how do you identify which one will be used for a certain question? You have to read through the question and find out the information available for you and use that information that is given by the question, and you should be able to identify which possibilities that you need to use. Now let's have a look at the first question. The question wants you to find the heat of combustion of glucose. So you need to find the heat of combustion for glucose. The question gives you the mass of glucose that is being burned inside a bomb calorimeter, and the temperature increase from 29.45 degrees Celsius to 31.44 degrees Celsius. Okay, and the questions also gives you the balanced thermochemical equation. Therefore, step number 1 will not going to be the writing up of balanced thermochemical equation, because it is already given by the question. So from the information given over here, 2.06 grams of glucose, we should be able to find the number of mole of glucose being burned in the bomb calorimeter. So the number of mole of glucose, when you work that out, you should be able to get 0.0114 mole. Okay, so that is the number of mole of glucose that has been burnt inside this bomb calorimeter. By finding out what is the number of mole of glucose, you will be given 1 mark. After that, you need to be thinking about which Q absorbed will be involved. Okay, remember we have 5 possible Q absorbed. So for this particular situation over here, what is the Q absorb equation or situation we need to use in order for you to find the heats of combustion? So when you look at the question carefully, you need to use the Q equals to mc delta T plus heat capacity big C delta T. We need to use this Q equation because the question gives you the information about about the specific heat capacity. So you have the information about specific heat capacity of water. Right here, you have the specific heat capacity of water been given to you. Also, the question gives you the information about heat capacity. You have the information about heat capacity, which is right over here, heat capacity, 814 joule per degree Celsius. You have 2 clues over here on why we need to use Q equals to mc delta T plus big C delta T. Now step 2, now we have found out what is the Q absorb that we need to use. We need to find what is Q. First of all, we need to look at what the question gives. The question gives the mass of water inside your bomb calorimeter, which is 982.0 grams. Okay, so that is the mass of water. The calorimeter contains 982 grams of water, so that is the information given. And you have the specific heat capacity equals to 4.184. That is the specific heat capacity. Okay, specific heat capacity is given to you as well. And you also have the heat capacity of the calorimeter. You have the heat capacity of the calorimeter, which is 814. And when you look at the temperature change, you have it from 29.45 degrees Celsius increased to 31.44 degrees Celsius. Okay, so the delta T or change in temperature would be 1.99 degree Celsius. So when you take all of these values and you're going to substitute in the Q equation that we have identified, we're going to use the Q equals to mass of water times the specific heat capacity of water times with the change in temperature plus heat capacity of the calorimeter times with the change in temperature. So this is the one that we're going to be using. We have all of the information that we need. Thus, okay, you're gonna substitute mass of water, which is 982, into here, and specific heat capacity of water, which is 4.184, there, delta T, and the heat capacity of the calorimeter would be C. Do you remember that this part of the Q is related to the heat absorbed by water inside your bomb calorimeter? Remember, your bomb calorimeter has water inside the container, and also the container can absorb certain amount of heat. So you have that right here. Okay, so when you substitute all the value inside, you get something like this, and the Q, the heat that we are looking for through this calculation is 9.769 times 10 to the power of 3 joule. When you get this, you get 1 mark. When you use the correct Q absorb equation, you will get another 1 mark, okay? So when you look there, that is the mass of water times with the specific heat capacity times with the delta T, 814 for the big C over here, which is the heat capacity, times with delta T. Okay, so step 3, we're going to use the Q over N, the heat over number of mole, to find the delta HC, the enthalpy of combustion. So we're going to substitute that into here. Okay, so you need to remember, for combustion, you need to have the negative sign in front. You have to have this negative sign in front because combustion process is always going to be this, is always going to be exothermic. That's why you need to put the negative sign in front there. And when you plug in the values that we have found out previously, you have the Q, which is 9.796 right here. And that is kilojoule over the number of mole of glucose that we have worked out initially right there. You put that into this equation and you will get the negative 859.3 kilojoule per mole. Okay, so this is the heat of combustion for 1 mole of glucose. So by doing this whole thing, you have 1 mark. Finally, to conclude your answer, you have to write the full thermochemical equation like this. Okay, so you have to write the correct thermochemical equation alongside with the delta HC that you have found. Don't forget the negative sign because this one is enthalpy of combustion. So this will give you 1 mark. Moving on to the second question. This question wants you to find out the mass of methanol being burned. So the question gives you the enthalpy of combustion equals to negative 726 kilojoule per mole. And we need to find out what is the mass of methanol being burned. In this case, we need to think about which Q absorbed equation we need to use. When you read the question carefully and thoroughly, the question only gives you the specific heat capacity of solution. You do not have heat capacity. Therefore, the Q equation that we need to use is Q equals to MC delta T. So it's slightly different from what we had done in the first one just now, because in the first example, we have specific heat capacity given to you and also the heat capacity given to you in the question. So that's the reason why we're going to use a slightly different Q absorb equation. Okay. So since the question gives specific heat capacity only, you don't have heat capacity given to you. So we're going to use this Q absorb formula. Now, before we can look at step number 1, we have to know what does the question give. Okay, you need to list down all the information given to you. So we have the mass of water being obtained, okay, because over here it says that the temperature of 500 centimeter cubic water contained in a copper beaker increased by 5.4 degrees Celsius. So the mass of water is that. And from the mass of water, we can work that out to find out the mass over here, okay? So you need to remember the mass over there refers to the, always referring to mass of H2O that will be absorbing the heat. So we're going to use the density of water. Is that here the question gives you the density of solution, so that is the same as the density of water, and you get 500 grams right there. So that is the so you get the mass of water, 500 grams, and we're going to substitute that later on into your Q equation. What else the question gives to us? So we have the specific heat capacity and the change in temperature equals to 5.4 degrees Celsius, because the question says here the temperature increased by 5.4 degrees Celsius. So we're going to substitute all the values that we have into the Q equation, and you will get something like this. It's quite straightforward, and you would have a value of Q equals to 11.34 kilojoule, and you get another 1 mark for using the correct Q equation. So moving on to step 2, what we need to do is we're going to use the delta HC equals to negative Q over mole of methanol to find the number of mole of methanol before we would be able to figure out what is the mass of methanol being burned. Over here, the question gives you the enthalpy of combustion already, which is negative 726, and the value Q equals to 11.34 kilojoule. This is the one that we have worked out previously over here. And you have to substitute the value inside. When you switch this to the other sides and this to the other side, you should be able to get the number of mole of methanol equals to 0.016. So for this, you will get 1 mark, and that one will give you another 1 mark as well. Okay, for step 3, we're going to find the mass of methanol by using the formula mole times molar mass. We have found out the number of mole of methanol being burned in the bomb calorimeter is 0.016 mole times with the molar mass of the methanol, and we would be able to get the mass of methanol equals to 0.51 grams. For this part, you should be able to get 1 mark for that and 1 mark for your final answer. Now, let's have a look at some hot questions. So over here, it's not a very long question, but it's quite tricky. What the question wants you to find is, you need to find the molar heat capacity of the water. But before that, you need to know how much heat required to raise the temperature of this much of water from 22 to 98 degrees Celsius. So the heat required, how you're going to find that? First of all, you need to be thinking about which Q absorb we need to use. And when I read the question only give specific heats of water. So when that is the only information we have, we're going to use the Q equals to MC delta T. And the reason is because only specific heat capacity of water is given. Okay, so we only have that piece of information. Therefore, we're going to use this Q absorb formula right there. Thus, the heat required when you use that formula, I'm just going to substitute all the information that we have in there. 250 grams of water, 4.184 specific heat capacity of the water, the delta T 98 minus 22, so that is that over here will be the delta T, and you're gonna put it in there to get Q value equals to 79.496 kilojoule. So by doing this, you get 1 mark for your final answer. And then you get 1 mark for using the correct Q absorb equation. Now the challenge is to find molar heat capacity of water. When you see the word molar, so it has got to do with mole. We know that for you to raise the temperature of 250 grams of water, you need 79.496 kilojoule. But what about for 1 mole? What about for 1 mole? So that is what the question wants over here. The questions over here wants you to find the heat for 1 mole. Okay? So because we need to do that, we need to change first the information of mass. Okay, so you're going to change that into mole. So you get 13.89 mole. So this is for the H2O. And we will compare with 1 mole. Okay, so when you compare that with 1 mole, when you do cross multiplication, you're going to cross multiplication times and divide. So in this case, you will be able to get 5.72 kilojoule per mole per degree Celsius. Okay, per degree Celsius right there. So that is the answer. So you get 1 mark for the proportionality and 1 mark for the final answer.